In this next module, I'm going to introduce you to the concept of covariance, and we'll talk about linear correlation. First of all, I want to review from last week. We talked about the fact that t-tests, ANOVA, linear correlation, and linear regression all belong to the same family of models. They're actually mathematically doing, all those tests are doing exactly the same thing. You can show that mathematically they are identical. We talked about some of the assumptions that all of those linear models have. One of the assumptions was that the outcome variable is normally distributed. Of course, it turns out that these models are quite robust against this assumption, as I showed you last week. We have something called the central limit theorem, which tells us that the means, remember t-test, ANOVA, linear regression are all looking at means, tells us that the means will be normally distributed if your sample size is large enough, even when the underlying trait that you're looking at is highly skewed. Eventually, the central limit theorem kicks in. You can't guarantee exactly where that's going to kick in. So if you're dealing with small samples under 100, you have to worry about the normality assumption. Usually, as long as our sample size is above 100, most times, unless you have an extremely skewed distribution, that central limit theorem will apply. But for small samples, we're going to worry about this, and I'll show you some ways to evaluate this normal assumption for linear regression. We also had an assumption called the homogeneity of variances. For the t-test and ANOVA, that assumption said that in different groups, in the different groups we were comparing, the variances across the different groups had to be the same. This week we're going to talk about linear correlation and linear regression. The assumption is the same, except we might be talking about now a continuous predictor. Instead of comparing groups, our predictor variable might also be continuous. So how this assumption works for continuous predictors is it says that the variances for the outcome variable have to be equal at all levels of the predictor variable. Again, models are quite robust against this assumption. That means if you have slight differences in the variances at different levels of the predictor variable, that's not going to be a big problem. We need to worry about this when there are really big violations of homogeneity of variances. I'm going to show you how to do something called residual analysis today to check this assumption for linear regression. But just keep these two assumptions in the back of your mind. I'm going to start here by talking about Pearson's correlation coefficient, which is again directly related to linear regression. So we've got a continuous outcome and we've got observations that are independent, and we want to compare a continuous predictor to that continuous outcome. So we have now both a continuous predictor and a continuous outcome variable. We're going to use Pearson's correlation coefficient. Just to give you an example, in the first week of the course, I showed you some data that I collected from my Stanford classes. I had a simple little data set of 50 observations, 50 students, and I had asked them questions about things like coffee drinking and their political bent. I'm showing you here some data relating to variables. In the first week of the course, I showed you how to look at one variable at a time. Today, we're going to be trying to relate variables to see how variables go together. Here I'm showing you on the x-axis is the variable political bent. I asked the students to rate themselves from 0 to 100, 0 being the most conservative, 100 being the most liberal. I also asked the students to rate their feelings about President Obama, whether it's favorable, whether they favor him or not. And so 0 was an unfavorable rating, 100 was the highest, the most favorable rating. Not surprisingly, as you would expect, as people's political bent went up towards 100, towards the more liberal end, their ratings of President Obama also went up towards 100. And you can see that relationship displayed here. There's definitely a strong relationship between your political leanings and how you feel about President Obama. Again, not surprisingly. How would we statistically evaluate this relationship? Now notice that the graphic is a great way to evaluate this relationship. We already know a ton just from plotting it. So all the stuff I'm going to be talking about today, where it's going to be very important to plot your variables, as you'll see. But what if we wanted to add one more piece of information, an actual statistic and a p-value to this graphic? What statistic could we use? Our statistical question here is the political bent of a person related to how they rate President Obama? So what's the outcome variable here? Because I graphed the ratings of Obama as the y variable, we're assuming that that's the outcome variable here. So the outcome here is the ratings of Obama on that scale from 0 to 100. It's a continuous variable. We of course have to ask the question, is it normally distributed? Well, let me show you the distribution. So here's the distribution for ratings of Obama. Here's the histogram. It turns out that it's not exactly a perfect normal curve, right? You can see there's a tiny bit of a left tail here. Those are the Republicans, right, in the class. But it's pretty close. We have 50 people, 50 observations in this data set. By the time you get 50 people, if you start with a distribution that's reasonably normal, even if it's a little bit off like this, there's pretty good guarantee that the central limit there is going to kick in. By the time I get to 50 people, when I start with something that's just a little off from normal here, the means are probably going to be normally distributed. So for my purposes, for this linear correlation evaluation, I'm going to call this close enough to a normal distribution. If I only had maybe 10 people in the sample, I might not think that this was close enough and I might worry about the normal assumption, but this is not that far off of a normal. And for 50 people, I'm going to say close enough. Are the observations correlated? No, I just have 50 independent students, remember, in this data set. Are we comparing groups here? No, in this case, the independent variable, last week we did all these statistical tests where we compared groups, but this week I'm talking about situations where the independent variable may not be groups, may not be categorical. It may be a continuous variable as it is here. So if you've got a continuous predictor and a continuous outcome variable, your outcome is normally distributed or close enough, and you have independence, then that leads us to Pearson's correlation coefficient. I've actually talked about the correlation coefficient already in week 5 of the course. I actually mentioned it last week as well. So as I mentioned, the correlation coefficient is a value that ranges from -1 to +1. +1 is perfect positive correlation. Here we can see that R, we represent the correlation coefficient, we abbreviate that as R. So we can see that R, the correlation coefficient, is 0.78. So that's pretty high. As you can see from the graphic, there is a strong correlation here. The p-value is less than 0.0001. The null hypothesis here is that R is 0, because an R of 0 would mean no correlation. So all the p-value tells us here is that we can be pretty confident that these two variables are really correlated, that there is some correlation here. I'm going to now walk you through where the correlation coefficient comes from. I haven't told you that yet in the course, so now I'm going to tell you where it comes from. So to understand the correlation coefficient, we have to actually go back and introduce a new concept called covariance. So let me start by talking about covariance, and then you'll see how covariance leads into the correlation coefficient. So here I'm going to start with the formula for covariance. The formula is actually instructive here. Covariance is evaluating the relationship between two variables. And if you look carefully at this covariance formula, you might recognize that it looks awfully similar to the formula for variance that I gave you in the first week of the course. And of course, the title covariance will give you a clue that it's related to variance. I'm just going to walk you through what this formula means, what it actually produces. What we're talking about here is when you've measured two variables on everyone in your data set. So xi and yi would represent, say you've measured height and weight on people. X1 and Y1 would be the height and the weight of the first person in your data set. So you've got pairs of heights and weights that are related because they belong to the same person. What are we doing with covariance? We're trying to estimate, we're trying to decide whether or not two variables are related to one another. Do they vary together? So imagine x is height and y is weight. And x bar, therefore, is the mean height in your sample, and y bar is the mean weight in your sample. Imagine you've got a person who's really tall. So that xi, imagine that xi is somebody who's, say, a foot above average. So if you do xi minus x bar for somebody who's really tall, you're going to get a positive deviation from the mean. If somebody's really tall, because height and weight tend to go together, if somebody's extremely tall, they are also likely to be heavier on average. So it's very likely that if you're very tall, you're also going to weigh more than average. That means the deviation for weight, yi minus y bar, is likely to also be positive. It won't always be, but if height and weight tend to go together positively, it will tend to be that you're going to end up, when you end up with a positive for the deviation for height, you will also end up with a positive for the deviation for weight. So when you multiply together two positives, of course, you get a positive. Now let's say you were a person who was short. So if then your deviation for height would tend to be negative, but because you're shorter, you'd probably also tend to weigh less, so it would be likely that your deviation for weight would also be negative. When you multiply together two negatives, you get a positive. So if two things are positively related to each other, like height and weight, the covariance will be something positive. Now let's take the case where we have two things that are inversely related, two variables that are inversely related. So say if you party a lot in college, perhaps your GPA will be lower, right? So if you're partying too much, you're not studying as much, maybe that will lower your GPA. Those things might be inversely related. So let's just say you're somebody who likes to party a lot, you're going to have your xi minus x bar, your deviation for partying, you're going to be above average on partying. So you're going to get a positive for xi minus x bar. But because you're above average on partying, maybe you're below average on GPA. So for your deviation for GPA, maybe you're going to get a negative. So what's a positive times a negative? Well, that's going to be a negative. And similarly, if you don't party as much, maybe your deviation for partying is negative. Maybe that means your GPA is going to be higher. A negative times a positive is again a negative. So two variables that are inversely related will have negative covariance. Finally, let's talk about two variables that are not related at all. So let's say height and your GPA in college. Probably not related. So let's say if your height is above average, well, it's kind of 50-50 whether or not your GPA is going to be above average. So maybe it's random, right? So you have maybe a 50% chance that you're going to be multiplying that positive times a negative here. So you have 50% chance that you're going to be below average on GPA. Then there's a 50% chance that you're going to be above average on GPA. So it's kind of a wash. Half the time when you multiply these deviations together, it's going to be negative, and half the time it's going to be positive. You add up all the negatives and positives, you're going to end up with a covariance of 0. So two variables that are not related will get a covariance of 0. So that's the idea with covariance. And I just want to point out again, this formula is very similar to the formula for variance. Remember, the formula for variance looks like this. It was xi minus x bar, the deviation for x, squared. So you can think of a variance as just a covariance between a variable with itself. So there's a direct similarity here, and this formula is not too hard to understand. Just to summarize, again, if x and y are independent variables, then the covariance will be 0. If x and y are positively correlated, then the covariance will be above 0, will be positive. If x and y are inversely correlated, then the covariance will be negative. Now notice that sounds awfully similar to what I told you earlier about the correlation coefficient. And indeed, there's a direct relationship between covariance and the correlation coefficient. For covariance, the problem with covariance as a measure is that it completely depends on the units. So think about what the units of covariance are going to be. If you're talking about the covariance between height and weight, say, your units will be something like kilograms times meters. Well, that's a little bit arbitrary. That means a covariance for height and weight is going to be different depending on whether you measure it in kilograms times meters as opposed to when you measure it in pounds times inches. So the covariance, that magnitude, is completely dependent on units, which makes it hard to understand covariance and interpret it directly or to compare it across different situations. So wouldn't it be nice if we had a measure that got rid of the units, that standardized covariance? And that's what a correlation coefficient is. If you divide the covariance by the standard deviation of x and the standard deviation of y, you are essentially dividing out the units. So again, if your covariance was in kilograms meters, well, the standard deviation of height is going to be the meters, and the standard deviation of weight is going to be the kilograms, so you'll divide out the kilograms and the meters. You'll end up with a unitless quantity. So it turns out if you divide the covariance by the standard deviation of x and the standard deviation of y, you divide out the units and you always end up with a value that will range between -1 and +1. And this is the Pearson's correlation coefficient, that measure that we've talked about earlier in the course. It's simply a standardized covariance. We could have just dealt directly with the covariance if there weren't this unit issue, but by standardizing, you are making something, a correlation coefficient, that has no units and something that always ranges between -1 and +1, it's comparable. You can compare it across many, many different situations, which is really nice. Again, the Pearson's correlation coefficient is just the standardized covariance, and I'm presenting the formula once again here. Again, you're probably not going to have to calculate this by hand, but if you ever wanted to calculate this by hand, this looks messy, but all this is the numerator is covariance, which I just showed you. And of course, you've already calculated in this course before the standard deviation, a standard deviation of a single variable, so the standard deviation of x and the standard deviation of y. So if you had to calculate this by hand, if you understand this conceptually, you should be able to calculate this by hand. Of course, it's very tedious to do this by hand, and you would, of course, do this on a computer. But I think the formula here helps you to understand the concept of covariance and correlation. So correlation, the one thing to keep in mind that people forget is that the correlation is actually measuring the strength of the linear relationship between two variables. I'm going to show you in a minute that if the relationship is something other than linear, the correlation might not be picked up by the correlation coefficient. The correlation coefficient ranges again between -1 and +1. 0 means no correlation, means your variables are independent. -1 means perfect inverse correlation. +1 means perfect positive correlation. So here's a picture that's showing you perfect positive correlation. That means that all of the dots lie on a single line. That would be the pictorial representation of an R of +1. If you have perfect inverse correlation, all the dots lie on the same line, but your slope is negative. You're going down. So that's the picture for that. I'm just going to draw you a few pictures here to illustrate correlation. So greater scatter around the line generally means weaker correlation. So let me just show you some pictures of what different correlations look like. So here's a situation. Imagine a situation where basically, if you know x, you pretty much can nail y, where everything, all of the dots are essentially on the same line. That would be an example, as I just showed you, of R of +1. If, however, there's a little bit of scatter around the line, that is, if you know x, you can get pretty close to y, but it's not perfect. They're not all perfectly on the same line, but you're still pretty tight around the line. That's going to be a strong correlation, maybe something of the magnitude of somewhere around 0.8. So that's a little bit of scatter, so it's not perfect correlation, but still very strong. However, if you have a lot of scatter around the line, kind of big scatter here, here's the best fit line, the line that kind of best fits those points, and there's just a lot of scatter around that. Well, that's going to be much weaker correlation, because now if you know x, there's still a lot of variation in what your outcome variable is going to be. There is some correlation here, but knowing x doesn't tell you so much about y. There's a lot of variability, and this might be something in the range of, let's say, 0.3. That's kind of a weak correlation. And of course, if you are talking about something that has a negative relationship, an inverse relationship, the slope is going to be in the other direction. This might be, say, something like an R of -0.6. It's negative because the slope is downward. There's an inverse relationship there. So that's just to give you a sense of what different R's, different correlations will look like. As I mentioned, the correlation coefficient measures linear correlation. Sometimes x and y are related, that is, they're not independent, but they don't have a linear relationship. So here's a nice simple example. Imagine that x and y have a beautiful quadratic relationship like this, right? This is a beautiful relationship. So clearly there's a direct relationship here between x and y. It's just that it's a quadratic relationship. If I were to try to fit a line to these points, guess what? The line is basically going to go right through the points, essentially having a slope of 0. My R, my correlation coefficient here, is going to come out to 0. I might, if I just calculated the correlation coefficient in the computer without plotting my data, I might look at that R and say, oh, x and y aren't related. But that's wrong. X and y are very strongly related in this case. It's just that they don't have a linear relationship, they have a quadratic relationship. So always keep that in mind, that the correlation coefficient is only going to capture linear relationships. That's why it's so important to always plot your data to evaluate, are x and y linearly related, because sometimes they're not. Finally, if you have two variables that are not correlated at all, the picture is going to look something like this. It's just completely random. X and y have nothing to do with one another. If you draw a line that best fits those points, of course, it's going to be flat. The slope is going to be 0, and the correlation is going to be 0, as we said. Back to my example data from my Stanford class. As I mentioned, the correlation coefficient between your political bent and your ratings of President Obama, not surprisingly, was high. It was strong correlation, 0.78. You can see that there's some scatter around the line, but it's a pretty strong relationship, highly statistically significant. I then went and looked at how does your political bent relate to not your ratings of Obama, but your ratings of the healthcare reform that just happened in America. Some people call it Obamacare. I asked the students to rate how they felt about that new healthcare law, the new healthcare reform, on a scale from 0 to 100. Now you'd expect, since the healthcare reform was largely supported by Obama and the Democrats in the US, you'd expect that your political bent would predict your feelings about the healthcare law. But you can see that that's true to some extent, but it's not as strong as a relationship as we saw in the last slide. It's a much weaker relationship. There's a lot of scatter here. You'll notice that it's certainly not a perfect relationship because, for example, I've got somebody over here who's pretty Republican, and they really like that healthcare law. And here's another Republican who's pretty favorable towards that healthcare law. On the other hand, I've got this really liberal person over here who doesn't like the healthcare law so much. So you can see there's a lot of variability. It tends to go up. Your feelings about the healthcare law tend to go up as you tend to get more liberal, but it's definitely a wide range here, and the correlation coefficient of 0.3 reflects that this is a weak correlation. It does come out to be statistically significant, which indicates that it's probably a real association. It's just that it's not totally tight. It's not very strong. I want to just show you, I showed you this graphic on the previous slide that I had put a line there. I had already put the best fit line in. The reason I want to show you the graphic without the line is notice that when the graphic has the line superimposed, when I've already asked the computer to draw that line on, it can be very misleading to the eye. If I had showed you this picture first, you might look at that and wonder if there really was any correlation at all there. Your eye can pick up that there's maybe a little bit of positive correlation, but this graphic much better represents just the kind of that it's fairly random. There's a little bit of a trend and association here, but it's pretty random. When you draw that line on, it can totally draw your eye to the line, and you can be misled to think that the correlation is stronger than it actually is. So just be careful about that. Always look at the picture without the line on top as well to make sure you're not getting misled. One final association that I wanted to look at was whether or not your political bent had anything to do with your optimism. You might think that since the Democrats running the country, maybe the Democrats would be more optimistic, or something like that. It turns out that there's no relationship between your political bent and your optimism, at least not in my class. So here I'm showing the correlation, and again the best fit line. You can see that it's pretty much random. How optimistic you are doesn't really have anything to do with your political bent. The correlation coefficient here comes out to be 0.09, which is pretty close to 0. The p-value is 0.57. Again, the null hypothesis here is that the correlation is 0. We clearly don't have any evidence to reject that null hypothesis. It looks like very well could be that the correlation coefficient here is right around 0. Again, that line is probably fooling you right now, and it's drawing your eye and making you think, oh, maybe there is a little bit of positive correlation. In fact, let me take the line off, and you can see that it's completely random. Really, there's no correlation here. That line is misleading your eye a bit.